Okay, so maybe we can start then. Okay, I'm a little bit spaced down. I'm afraid I overslept a little bit this morning, so I apologize. My apology in advance for every stupid thing I can say. So let me just recap slightly what I've been discussing up to here. Essentially, the basic idea is that one wants to study statistical properties of dynamical system, and essentially the strategy was in two steps. One step was dynamical, and consisted in essentially establishing some kind of weak dependence. And so weak dependence, I mean, these are just, I was seeing the object that I was looking at as a random variable, and weak dependence means some decay of correlation. And I discussed the fact that this sense in which there is decay of correlation is not exactly the normal one to which people that maybe do Markov process are used, but it's some kind of weak dependence that you can establish, and then you have a probabilistic approach, which consisted essentially in copying. Copying what people do in probability. That's various ideas, and they can be, once you take this point of view that essentially your dynamical system is a Markov chain, you can try to reproduce the same type of arguments that are done for Markov chain. And I showed three possibilities that could be used in order to, for example, study the central limit theorem. Of course, this example I was looking at was extremely simple, so it was a little bit like shooting to a fly with a cannon, but still, I mean, the principle was okay, right? The principle is just that this technique could be applied there, so maybe they can be applied in more reasonable system. Now, the next step, I wanted to just try to go on and talk about a little bit more reasonable systems, but of course now, I mean, which direction one wants to move. So I have, of course, my personal idiosyncratic point of view about the universe, and it comes mostly from the fact that I have been trained in statistical mechanics, although I know very little about statistical mechanics, but that is the fault of the student, not of the teacher. And so that is kind of the direction in which I would like to move. Of course, my typical conversation with the physicist is a little bit frustrating because I just explained, yes, I would like to obtain statistical mechanics starting from deterministic system. So they say, oh, that's very interesting. And I say, okay, but I can do it only for very small system. And then they say, okay, small system are okay, maybe, you know, like 10 to the 9 particle, let's say 10 to the 10 degree of freedom will be very good. And how many degree of freedom can you do? And they say, well, maybe 3. And then they look at me like, what kind of moron are you? I mean, what are you talking about? And of course, I understand that there is no statistical mechanics if you don't have a lot of degree of freedom, although people like Galavotti and Ruel have been heard to argue otherwise, but nevertheless, I mean, I know I have Stefano that he's a staunch supporter of this point of view, that you have to have many degrees of freedom. I kind of agree with him. And yet, if you want to run a marathon, you have at least to know how to walk, right? Because otherwise, your probability of running long distance is not very good. So for me, this is what I would like to do now, present just my point of view on this stuff, but the statistical mechanics is kind of a very distant place that just gives me the direction in which I want to go. And of course, I'm very aware that I will die before getting anywhere close. But at least, I mean, the idea is to get closer. So I started with a model that is very reasonable for statistical mechanics, much more reasonable than what I discussed. It was the Lorentz gas. And I would like to introduce some facts that exist in the Lorentz-Gas, and in this model of the expanding map that I discussed, they are not there. So first of all, I want to go to higher dimension. And I want to have reversibility. So higher dimension, I mean, I told you I will do small step, 2, okay, from 1 to 2, okay. So let me go from 1 to 2 for the moment, and I want, of course, to maintain the key properties that work for me here, which is the strong dependence from initial condition. Okay, strong dependence from initial condition, as I told you before, it means that if you have two nearby initial conditions, they will diverge exponentially. But now I have reversibility. It means that if there is some kind of transformation in phase space, that if I apply this transformation in the Lorentz-Gas is simply reversing velocity, then the system, the dynamics which correspond to the dynamics going backward in time. Okay? So if I have strong dependence of initial condition, it means that I have initial conditions that diverge, but then if I do this time reversal, this will converge. So it means that if I have a time reversible system, then necessarily, if I have the mechanism of strong divergence with respect to the initial conditions, then there also must be some initial conditions that, on the contrary, converge. And then they have the future that is similar. Of course, this seems a little bit strange because, okay, now I want this mechanism of divergence, and because of that, I automatically get a mechanism of convergence. So it's kind of confusing, but let me just take the basic example so you understand that satisfies this, that you understand what is going on. So I wrote it already, but let me write it again. Okay, this is a toral automorphism, is a linear diffeomorphism of the two torus, and sometimes it's called the Arnold cat, as though probably it's not very good now because there is all this emphasis on animalism and stuff. In Italy, I just learned that Berlusconi decided to start a party that is based on defending the right of animals. So, of course, to take a cat and squeeze it like that is not good, at least for him. But that's actually is a good reason to discuss this example. OK, now, I have this system. And if you look at, so this is just the action of the matrix mod 1. And of course, this matrix, if you look at it, first of all, the determinant is 1. So the back measure is preserved. That's good. So you have a preserved measure. And let's call this matrix A. There are two vectors, A, V, U, lambda equal lambda, eigenvector. So this, I call it the unstable eigenvector. So this is in a direction in which I do have this phenomena, that if I have two points that their distance is along VU, they will be stretched. Their distance will increase by lambda at each time step. Lambda is bigger than 1. You can compute what lambda is if you want. It's just a nice number that has to do with the gold section. The gold ratio, sorry. And of course, because of reversibility, I know that there should be also an eigenvalue with lambda, with eigenvalue smaller than 1. And indeed, there is some Vs that is equal to z, because determinant is 1. OK. Here, reversibility corresponds to exchanging x and y in some way. I mean, there is some involution that conjugates this map with the inverse map, which is just a rotation of 90 degrees, essentially, right? It's just corresponding to exchange these two guys. Now, so what does it mean? It means that, you see, if I take any vector, okay, then I have, wonderful, I have even, okay, let's make the unstable direction red and the stable direction blue. So if you take a vector, of course you can decompose it in the stable and the unstable part, and so you will get that the stable part will be expanded from here will go to here, and this from here will go to here, so the new vector will be something like this. This is a point, and this is the image point. So you see, you just apply the dynamics, and you kind of, any vector tend to go toward the unstable direction. And of course, if you have 2 points here, one here and one here, then their distance grows. So it means that if you have essentially any 2 points more or less at random, their distance will grow. But if you are so unlucky as to take 2 points that are aligned, very closely aligned to the stable direction, then their distance will shrink. Okay, and now when I say at random, of course, I imply that there is some kind of probability measure. Here I'm thinking I'm at random, like maybe with respect to Lebesgue. But of course, this is a problem, no? Because if you take a probability measure and you push it with the dynamics, and then you reverse, then you go to the probability measure you started with. So it means that pushing with the dynamics, you get a probability measure for which you see something strange that you do not expect. Because you expect typically things to diverge. But of course, if you push with the dynamics with this measure with this dynamics, at a certain point you get some measure. Now you take the time reverse, and this somewhat is not a measure that you see physically, because this corresponds to behavior in which things tend to go together instead than typically go together instead than diverge. And that corresponds to the fact that is actually, if you think a little bit, if you get a gas of particle, of course, you can get, in principle, you can get a gas of particles that behave in a completely crazy way, like instead of expanding, just contracts. Or you start with some bunch of particles, and then they collide, they interact, and then they just dissipate. But of course, if you reverse velocities, this will just concentrate, which is something that you don't see. But the point is that this reversing of velocity is something that you don't know exactly how to do physically, right? I mean, you go in a lab, and how the hell are you going to reverse velocity? So the fact is that these measures that you get out of, taking some reasonable measure, like absolutely continuous with respect to the bag, and then waiting for some time to see what the gas does. If you take this measure and you reverse, then you take a measure, you get a measure for which you see something unphysical, but is a measure that is essentially impossible to construct in a lab. So I mean, that's kind of, so in some sense, the initial condition knows something about the universe, right? And the initial condition has knowledge about the direction of time in this situation. So let me just discuss here a little bit what's going on in this example. Because the first, I want to discuss the dynamics part. Dynamics part, we saw that this weak dependence was coming from the fact that the system was mixing, meaning that if I was starting with a measure that was absolutely continuous with respect to Lebesgue, the system, and pushing this measure with the dynamics was converging to the invariant measure. And in which way it was converging? It was converging in, so you had convergence in W11. That's what I proved. So it means that you have a measure, some initial measure. So you have an initial measure, rho dx, and then you push forward it with the, in my case, I push the measure with the dynamics, so that means that I push the density with the transfer operator, and then this was converging to rho star dx, which was the unique invariant measure. So, and this convergence was happening in W11. So no dx now here. Okay. So that is kind of, it's a reasonable strong convergence. Okay, it's not convergence in L2, but Yeah, this is a reasonable strong convergence. So the problem is that it doesn't work. It works only if rho is in W11. So if you have a function that is not very smooth, then you don't have the convergence. Like, for example, if you start with a delta function, you don't converge anywhere. But still, I mean, that is the type of convergence that you get. The convergence is kind of strong. And now let us see what kind of convergence we can expect in this example. Let me just forget the moment that I am in the torus and analyze only the linear part, the linear action, right? So imagine that I just rotate this picture. So I have the stable direction that is this one, and the unstable direction, okay, that is this one. So I've just rotated the picture. So in this coordinate, my matrix becomes lambda 0, 0, lambda minus 1. Okay. Let's call this matrix B. It's just conjugated to my original matrix. I'm just rotating the coordinate. There is one direction in which I expand, is this one, and one direction in which I contract, it is in this one. And now I take some density. Let's say I take 1 plus alpha sine y. Okay, so this is x coordinate, this is y coordinate. Okay? I take alpha sine y, this is x, y. Okay? And now I want to see what happened to this density. Very well, I want to see what happened to this density. I have to see what is the transfer operator in my case. In my case, the transfer operator, you remember, this guy comes from a change of variable. And in general, it had the formula sum of the preimage, but there is only one preimage. So it is just rho compose f minus 1. And then there is, divided by the change of variables, there is the derivative of df compose f minus 1. Okay? Because you have to do a change of variable in 2 dimensions instead that in 1 dimension, so you get the determinant of the derivative. And that is the transfer operator in higher dimension, in 2 dimensions, for an invertible map. But in my particular case, this guy is not there because the determinant of the derivative is 1. The matrix has determinant 1. So my transfer operator is simply the conjugation with the inverse map. So it means that if I apply L rho, then this is just 1, because, and then I have plus alpha sine of what? Of the inverse map. It is just b minus 1 equal lambda minus 1, 0, 0, lambda. So this will be lambda 1. Okay. And that is the new density. I mean, it's a little bit, it's a local picture, right? Because on the torus, everything wraps around. But locally, that's what happened. And now you want to see what happened. You want to look at phi compose Fn time rho, okay? And you want to see what happened to this thing. So forget about, let's imagine that you are on the universal cover that is R. So, and forget that on R this is kind of ridiculous because, I mean, this is not a probability measure. Just look at just what happened locally. And what happened locally is the following. You get this is 1, okay? So this is just the integral of phi, which this is kind of the invariant measure, okay? Because the invariant measure is Lebesgue. And then you get alpha sine lambda y phi x y dy. And if you write this in Fourier transform, this is essentially a Fourier coefficient. So you get this is the Fourier coefficient, more or less, at lambda. And if phi is kind of regular, this will go to 0. Sorry? Lambda to the n. Sorry, you are right. Lambda to the n. So the Fourier coefficient goes to 0. But that's what it's telling you. It's telling you that, okay, this converges to that, but only weakly. Because, I mean, this guy in itself doesn't converge anywhere, right? It just oscillates more and more and more. In the unstable direction, you see, if I had also add cosine if this was time cosine x, then here it will be cosine minus nx. Okay, so this converges to 1 when n goes to infinity. So that's perfectly okay, because that is exactly the expanding part of the dynamics. And for the expanding part of the dynamics, I have a reasonable convergence, pointwise. But for the other part of the dynamics that I have to have, the part that is contracting, then, I mean, my density just, as if it has a sort of an oscillation, it will just oscillate more and more and more and more. And it doesn't converge anywhere pointwise. But weakly, yes. This is just Riemann-Lebesgue, right, essentially. Just you integrate against the functions that oscillate a lot, and then you see only the average. So that means that once you step up in this situation, the sense in which you have the weak dependence gets even more tricky, because now the convergence to the invariant measure will be only in some weak sense. And now you have to understand what to do, because can you kind of upgrade this view of studying the spectrum of the transfer operator in this context? If you do that, of course, you cannot hope to have a space of regular function, right? Because if you are so crazy as to say, okay, let's look, so this operator, how does it look? In L2, the operator now is just this one, like L rho equal rho compose F minus 1. Now, in L2, this is a computation that I did it already. Let me do it again. Now, the Lebesgue measure is invariant, so I can change variable. And then I get an isometry. So it means that in L2, the spectrum of this operator is just the unit circle. And that's it. That is. So this was more or less known for a very long time. If you look at the work of, well, again, what is this book in which they do the study of, I mean, okay. So this goes back at least to von Neumann, right? Because if you look at the weak-ergodic theorem of von Neumann, his strategy is exactly to look not at this operator, but at the operator, at this operator in L2. That's what von Neumann does. So this is just the adjoint of the transfer operator, and this is called the Koopman operator. So von Neumann looks at the Koopman operator in L2, and then he uses that to produce his ergodic theorem. Okay. Now, and then there has been a lot of activity in the Russian school studying this operator and seeing the spectrum of this operator and so forth, and so on and so forth. There is some, actually, almost a book that is, I forgot, maybe, in which is discussed all these type of spectrums that you can have. Because you see, since it is L2, then you have some nice fact. You can look at the spectral measure. And then studying the spectral measure, you can connect the spectral measure with property like ergodicity, mixing, and so on and so forth. Right? That's very good, but you get only qualitative information, like mixing, Bernoulli property, stuff like that. There is, as far as I can see, there is no way to get quantitative information like speed of mixing out of this picture looking at the operator in L2. And of course, the strategy that was used to get speed of mixing was to use Markov partition and to code the system somewhat. But that turned out to have some limitation at the end. It's a very effective technique indeed, but at a certain point it does have some limitation. And so one would like to know if is a way to instead use this different technique that is based on the study of the spectrum of this operator, kind of more direct. You don't code the system, you don't do anything. So this essentially has been kind So what do you want to do, essentially? You want to find the Banach space, maybe an Hilbert space, but or some space in which you see the operator, let's say a Banach space, on which you see this operator acting. And it would be good to have two Banach spaces, because I would like to mimic what I've done. I had L1 and W11. So I would like to have two Banach spaces, a Banach space, weak Banach space that contains a strong Banach space, and the operator acts on both, and in a nice bounded operator, both in L, B, B, and in L, BW, BW. And then hopefully in this Banach space I have this Lasota-York inequality, and then I can get, I can copy what I've done in one dimension. I mean, I get the spectral decomposition and so on and so forth. So that is the idea. The question is that, do such Banach spaces exist? And that was not very clear till rather recently. I think that the first paper in which this was done really completely is a paper. There were several papers before, but this is just a paper of 2002 by Blank, Keller, and myself. Now, let me just try to explain you. Now, this was just the beginning, so this is rather recent stuff. It's just 15 years ago. But in the meantime, we went from the situation, from wondering, are there Banach spaces that do the job that we want, to the situation, oh my God, there are too many of these Banach spaces, which one is the right one? Okay, so that is because several people contributed, and now there are at least 3 or 4 different versions, and all have some advantages, some disadvantages, so it's kind of situation is not totally clear what is the right way to go. But let me just, since I don't want to enter in such a discussion, let me just keep things simple, and let me describe to you a version that is called the geometric version, that essentially is the one that was more or less presented in this paper. I mean, not really, but essentially. Because essentially there are two versions. One is this called geometric version that I will present. Another one is based on trying to analyze the Fourier transform of the function. So it is just some kind of Sobolev Banach spaces, but of course they are a bit strange because they must be anisotropic. You see, the problem with these Banach spaces is that there are different directions. In one direction something happening, in another direction it happens something different. So the Banach space, the norm of the Banach space must know about this geometry of the system. So it cannot be isotropic. It must distinguish direction, right? So you can, of course, do anisotropic Banach spaces in Fourier norm. These are just, I don't know, triple space are called. But then more recently, so this was kind of initiated by Vivian Baladi, but then more recently people from, how is it called? Microlocal analysis, essentially, entered in the business, and they kind of used techniques that are used in quantum mechanics to see that, in fact, these operators are not so different from the operators that are studied, for example, in random scattering in quantum mechanics. And so now there is all kind of business like in which people use kind of different techniques. But the idea is always the same. There are two directions, and you have to somewhat distinguish these two directions. So let me just keep it simple, because I want just to give you the idea, not the technique. So let's just say that I take pieces of stable curves. What is a piece of a stable curve? A piece of a stable curve, so here there is this matrix as a stable direction, which was this one. Okay, sorry, it was this one. Okay, so a stable curve is something, it's like a little bit like this Dolgopiat standard pair. You choose some scale delta, small, okay, and now you take a curve that is in the stable direction and is long more or less delta, between delta and 2 delta, let's say, right? And now you push this curve with the inverse dynamics, and what will happen? It will get longer. Okay? Now, notice that now you can be upset with me because you say, you just explained to me that it's very hard to identify this stable direction because this is not very natural. But that's not the point, because here you're pushing with the inverse dynamics. So this is kind of a natural direction for the inverse dynamic. If you take something that is a little bit off, then this also will be aligned to that. So it doesn't really matter from where you start. But
so you take not unstable directions, which are here just straight.
Yes.
Okay,
so I mentioned yesterday that there are two kinds of technique that can be used in parallel. One is this Dolgopiat standard pair, and the other one is this transfer operator business. These techniques are kind of the dual, one of the dual of the other in some sense. So Dolgopiat will take a segment of unstable direction. Here instead, what I do, because that will be invariant for the forward dynamics. Here instead I take a segment of stable direction. And this is invariant for the backward dynamics, okay? Just because I'm integrating, so I mean, the operator goes backward.
These examples are straight lines.
Yes, it's a segment, just a segment, right, of length delta. In these examples, they are just a segment of length delta. And now, what is interesting of this curve is that I take one of these curves, I push it backward, it gets longer, and then I can divide it, okay, in curves that are of the same type. Okay, so I can write the image as some sum of curves that are, or some union of curves that are of the same type. So there is some invariance in these curves. Okay, and now let me just consider this just to show you. So now I have this set of curves, right? This set of segments, I call them gamma. Okay. These are all segments of length between delta and 2 delta. Okay, and now I take the integral of gamma, and then I take some function phi, and then I have my density rho. Okay, and now this I can take, I look at this object, and let me see, this is very similar to what I did, the computations that I just did, but let me see what happened to this object when I apply the transfer operator to it. To the density. Now we want to compute this object, but not for the density at time 0, for the density at time 1. Okay, no, now this is equal to the integral of gamma of phi, and then I have rho compose f minus 1. Now I can change variable, and what do I get? Well, the change of variable, I will get, I want to change variable, let me just write, this will be from 0 to a, where a is between, so this curve will look like this. I have a base point, let's call this base point C, and then this point will be C plus A Vs, because this is the stable direction, right? I erase it. So that's how it looks like, very well. So now I have the integral from 0 to A will be between delta and 2 delta. I mean, that depends which curve I have chosen. So the curve depends essentially from the base point and A. That is, classify all my curves, right? Now, this will be phi of Xi plus S Vs, and then I have rho of Xi plus, is attached to Z. So this is f minus 1 of Xi plus lambda S Vs ds. Okay? That is what it is, because if I apply to this point, to a point here, which is the point Xi plus S Vs, I apply the map f minus 1, then this point goes to the point f minus 1 xc. This segment goes again in the stable direction. Now it is longer. And this point here will go to this point. And the only thing that will happen is that the distance from this point here, which is the image of that, and from this will just be longer. It will just, this distance here was s, and here is lambda s. So that is what I wrote here. And now you change variable. So you change variable, your new variable is lambda s. So that means that now you get an integral from from 0 to lambda a, and then you have phi of xc plus xc plus lambda minus 1 s ds, and then you have rho of f minus 1 of c dxc. Okay? So, and then maybe you want to write this as f of f minus 1. Okay? So it means that now you have a different curve. You have a curve, this curve here, you have a curve based at f minus 1 of xc. This curve is much longer now, is longer, is lambda a, now the length of this curve. And you are integrating along, so this curve, I call it f minus 1 gamma. And this curve, now it is the integral from on f minus 1 gamma of what? Of phi composed f, essentially, rho. That is what I'm integrating, right? Because, sorry, this is plus s vs. I change variables, so this is just, I'm just integrating, instead of integrating this thing, I can integrate this thing, which is just the dual operator. Sorry, again. And of course, here there is, I forgot, there is a change of variable, so the Jacobian is lambda minus 1. Okay. So I'm just integrating this function that is just the dual operator along the image curve, and then I have some factor here. That here is constant, in general is not constant, it's just the Jacobian of the change of course. And the point of that is that now I want to write this again in form of curves that are allowed, that are in capital gamma. So this is going to be the sum over I, so I do some decomposition like this, no? And then it will be the sum over I of lambda minus 1, the integral of gamma I, and then I will have phi compose f rho. Okay? So now you see, I start with objects that are of this form, and I get to convex combination of objects that are of this form. And how many pieces do I have? Well, I have more or less lambda pieces, and I have this, which is lambda minus 1. So essentially, this means that if I start with some object like that, then I get again more or less object of the same type. And now the question is that if I want to look at weak convergence, then I should look at weak convergence. It means that this integral is okay, provided that it has some regularity. Then phi has some regularity. Because after all, you see, what happened? It happens that here I have essentially this operator acting on phi. But I can imagine that this operator is the transfer operator of f minus 1. But then f minus 1 in this direction is expanding. So essentially this behaves like an expanding map. This is like the transfer operator of an expanding map if I restrict myself to this direction. So here I would expect that this behaves well if phi is in some regularity class. So let me just take here the soup of all the phi that in C1. So phi is a function that is defined on gamma, right? So C1 of gamma is less or equal than 1. And now let me just compute the derivative of this one. Okay, so this one I can interpret as phi compose f. I can interpret it as a function on C1 of gamma I on gamma I, right? So this is a function on gamma I, very well. And now I want to know what is the norm. Well, the sup norm is the same. Okay, and the derivative, let me compute the derivative. This, I take the sup norm of the derivative, and that is clearly less. Now, this is the derivative of f, but remember, here we are exactly in the stable direction. So it means that it will contract. So it means that the C1 norm does not increase. So it means that this is less or equal than the sum over I, lambda minus 1, and then here I have the sup over the phi in C1 gamma I, more or equal than 1, of rho. Sorry, of this integral. And now, why don't I take also the sup on all the gamma? Okay, if I take also the sup in all the gamma, then here I can put also this will be also the sup on all the gamma. It doesn't matter. Because I just say that if small gamma is in capital gamma, then this gamma I will be in capital gamma, so this is what it is. So it means that, and now you look at this is a norm. This is a norm. So I can decide that this is the norm of rho. I call it the stable one norm, just to give it a name. And then this computation shows that this is less or equal, because this is again the norm of rho. So this is less or equal. I have exactly lambda p's. Well, maybe there is a factor 2, but I mean, if you do n here, the computation is exactly the same. Only here you have n, and 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 here you have n. And here you have n. And now this is exactly the same computation, but the point is that how many pieces you have? Well, the pieces at most will be, it depends how you cut, right? Because the pieces are not exactly of length delta in this game. They are between delta and 2 delta. Because the problem is that if you take them exactly of length delta, then the problem is that maybe you cannot cut, right? Because you get something that here is less 1, and then here it will be length of square root of 5. And then, yep. You want to say something, Jonathan? Yeah. Yeah.
It's slightly technical.
Yeah.
So, I mean, I understand you have, on the right-hand side of that definition, you have n's. On the left-hand side, you have no n's. I understand that somehow in the limit, I mean, if they balance, then you should be okay, right? But how do you formally set it up? I mean, right? Because which gammas are you using, right? Gammas that you got on the nth level, no?
So that's exactly what I was trying to explain. So, okay, so the point is the following. Now I do it for n, okay, and I get something that is less delta. It will go to length delta n. Okay, so now I have this thing, and what do? I say, okay, I have this thing that has this length, and now I start. This is length delta, this is length delta, this is length delta, this is length delta, 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 delta. And then I arrive at the end, and I get a piece that maybe is not good. So here I have a choice. I just say, okay, this piece is too good. Well, it doesn't matter. I take this one, and now this one is less than 2 delta. Okay, and now I have made my, it's just one way. It's not the only way. But it's one partition, one way in which you have gotten the division in intervals that are between delta and 2 delta. And how many are they? Well, how many are they? They will be lambda n integer plus 1, some stuff like that, right? So it means that when you multiply by lambda n by this by that, because this is the factors that you have, and this is the number of pieces. The number of pieces is lambda n plus 1, something like that. So this is bounded by, well, 1 plus something, by 2. Okay.
So you define this norm as the limit.
No. The norm is defined exactly like this. This is the definition. The definition of the norm is the soup on all the curve, the soup on all the function, and that is the norm. Ah, sorry, fuck. Sorry. Yes, so this is the norm of Ln. Ah, that's why, sorry. That was the norm of Ln. The norm of rho S1 is, sorry, Jonathan, I was just missing. This is the norm, okay? Gamma is length between delta and 2 delta. That is what the definition of this set here. These are gamma, they are like this. The gamma that I'm taking, they are like Xi is in the torus, and then I take the curve Xi plus S Vs in the stable direction with S in some interval I, and the length of I is in the interval delta to delta. That is the set of curves I'm considering, right? Take a base point and then move in the stable direction for a distance that is between delta and 2 delta. Maybe you want to take it close, I don't know. Doesn't matter. Okay? So that, yeah, delta is something that you fix once and for all. Typically, you have to do some proof at a certain point because you are a mathematician, and then you discover that delta must be smaller than something, but maybe 10 to 1/3, or maybe 1/5, doesn't matter, or maybe 10 to the minus 20, but something fixed. I mean, maybe very small, but it depends from the proof. I mean, but essentially, you will. In this case, it doesn't matter at all. You can take anything, it will work. You can take 200, and it will be okay. But you have to fix some scale. Okay. So this was a computation just to let you see that it is possible to cook up a norm and therefore a Banach space in which the transfer operator is bounded. Okay, but that you are not very impressed with because, okay, that also L2 has this property. Fine. But now let's take another norm. Okay? Because you want to see some improvement, like in the Lasota-York inequality. So I should produce at least a semi-norm that gets better. And now here is a semi-norm that gets better. This I call it U1. So let me just say that, let me just be a little bit more general. If you take, instead of taking functions that have C1 norm, you take functions that have CQ norm, the computation is exactly the same. Because when you try to compute the derivative, the second derivative, then you get lambda minus 2. So it's also that is good, right? So this is, you can put here any P or Q, any number, any positive number, and this is still a norm. Okay. And now I want to define a stable norm. So the stable, the unstable norm. So I call it the stable norm because you see, you just see what happened in the stable direction. And I do the same, but now I want to get some information on what happens in the unstable direction. So I just take here C1, let's say, well, let's say P. Anyhow, no, let's not make it complicated. C1 gamma, less or equals than 1. And then I have the integral of gamma, and then I have phi. And now here, I want to get some information on the regularity of this in the stable direction, because I know that the density in the stable direction should behave well. So I just will take the derivative in the stable direction. So this is just Vu, the gradient of rho. And this is my norm. Okay? So this is just a semi-norm, because if you take Lebesgue, the gradient is 0, and then you get 0. So it's just a semi-norm, but still is something that gives you information on how this function behaves in the unstable direction. And now you do the computation, which is more or less the same computation that I did here. But the point is that, you see, now you are taking, when you look at that, you have to take the soups. Okay, let me write all these soups, and then you have the integral of gamma, and then you have phi, and then you have Vu, and then you have the gradient of rho composed f minus 1. But this is what it is. This is exactly like the derivative of f minus 1 applied to v, and then is the gradient of rho composed f minus 1. Yeah, because if you have the gradient of rho composed f minus 1, then you apply the chain rule, and then you get the derivative of f minus 1, and then you put it on the other side, and then you get this formula. And now this, what it is the action of the inverse acting on the unstable direction. So this will contract, because the forward map expands in the unstable direction. So this is equal to lambda minus 1, and then you can take this away. And now you are exactly in the same computation as before, only instead of having rho here, you have this gradient. So you can put this outside, it doesn't make any difference. So it's exactly the same computation that I did here. Instead of having this rho, you have this quantity. Okay, fine. Then it means that it is contracting, and now this means that if you take, this is less, okay, let's do it n, and then you get n here, and then this is less or equal than lambda to the minus n, maybe it's time 2, some constant, time rho u1. Okay, so you see now I got some improvement. Okay, that looks very nice. And now, I mean, I would have to spend some more time in order to tell you how this is an improvement in the stable direction. I have to get an improvement in the unstable direction. In the stable direction. The problem is that you see here, why I didn't gain anything here. Here I got some gain. Here I didn't gain anything. The reason why I didn't gain anything is that because this is a norm, it's not a semi-norm. You see, this is the guy that is guilty for not improving. This improves. Here I have lambda minus 1. This instead remain, but this is okay, because I know that my transfer operator, I cannot hope to have a norm in which the transfer operator is a strict contraction, because I know that 1 is in the spectrum. So the spectral radius must be 1. It cannot be smaller than 1. So it means that I have to take advantage of this and pay a price in something like that. So I don't want to enter in the details, because that will take all the rest of the time that I have, and I wanted to tell you something more. So let me just tell you what are the norms. The norms are the following. Rho, this is the norm of the strong Banach space. It will be rho u1 plus rho s1. This is a norm. And the weak norm instead will be rho s2. So this, you see, is a distribution of higher order. It's like, you know, if you have the dual of C1 and the dual of C2. Okay, so that is what it is. I just test in the stable direction, but with functions that are a little bit smoother. Okay. And the idea is that you do this computation. Now imagine that you have, okay, let me tell you just one thing. Imagine that now you have 2 here. And you reduce this computation, right? But when you arrive here, you do the following trick. You write phi as, sorry, it was okay, you have 1. So you know that for this norm with 2 is kind of bounded, so it has this property, with 2 is okay. But now I want to get some gain, in the case in which here there is 1. And when I'm here, I write phi as phi epsilon plus phi minus phi epsilon, where this guy is in C2. Okay? And this is small. So it means that now this part, it will just be a part that it will just give rise, the phi epsilon will just give rise to some norm of rho in this sense. And then I can continue my computation having, for the function phi minus phi epsilon instead than the function phi. Is exactly the same computation. But the point is that now here is okay, because I want to look at the norm of phi minus phi epsilon. And essentially I get a factor 2, but then I get a lambda minus 1. But here, the sup norm of phi minus phi epsilon now will be small, because phi epsilon, I can take it as close to phi as much as I want. It's just, I have a C1 function, and I approximate it with a C2 function. So I can take this smaller than epsilon. Okay? And now I get that since this, now I have, let's say, phi hat epsilon, that is phi minus phi epsilon. And phi hat epsilon has this norm that now is smaller than epsilon, the norm of phi. And this guy instead, this guy, it has lambda minus 1, but it has maybe, I have 2 pieces, right? This and this. And the C1 norm of this is smaller than, and the C1 norm of this is more or less equal to this, so I get a 2. Okay. And then if you put an n here, 2 is always 2, so you get to the minus n. So now you choose epsilon to equal to that, and you have a contraction. So that is more or less the idea in which these norms are used. And so what you get the following. That L to the n rho S2 is less or equal than some constant rho S2, and L to the n rho is less or equal than some maybe 2 lambda to the minus n rho plus some constant b rho S2. And these are the Lasota-York inequality, again, for this strange space. And now all what you have to check is that, in fact, the unit ball in this norm is compact in this Banach space. And this is kind of easy to check. So now you are exactly in the situation that we were for one dimensional map, and we know that the spectrum of the operator L in this particular Banach space, it is 1. There is no other eigenvalue on the unit circle. There is some spectral here that turn out to be lambda, the square root of lambda, minus 1, so 1 over square root of lambda. That you have to check what it is, but essentially you get that, which is a bit strange because this is the square root, but that's what happened. Well, what gives me the square root? No, sorry, you are right. There is, so in this particular case, there is no square root. The square root happens, sorry, no, sorry. I was just thinking about another situation. What happens when the map phi is not infinitely differentiable? So if the map phi is not infinitely differentiable, then the differentiability appears here in some way. But sorry, I had in mind different things. So this is just lambda minus 1, and then outside there are finitely many eigenvalues of finite multiples. So essentially, you recover exactly the same picture that you had for expanding map. The only difference is that now the space on which you get this spectral picture is a bit strange. Okay, but it's inevitable because, yeah? Yes, I defined two norms, this and that. Oh, sorry, weak. This I want to call the weak norm. I wanted to use the same notation that I used when I stated the other day the general theorem. If you remember, I stated the general theorem by Enion, saying that if you have two norms, one strong, one weak, and you have this inequality, and then you have the Banach space B and the Banach space BW, this comes with this norm, this comes with this norm, then if the operator L is compact from B to BW and compact, and you have this inequality, then it follows the spectral picture over there. Okay. So that is kind of the drift that you have to that one can use in order to study system in this way. So just trying to show. I didn't say all the details. But essentially, in this case, I said all the details. But this case is very stupid, right? Because you can compute in Fourier transform. So if you compute in Fourier transform, you see the same phenomena. You see that when you iterate, certain Fourier coefficient goes to 0, certain other Fourier coefficient explode, and then you see what's going on very easily. But essentially, the situation is the same. The space cannot be a space of regular function, must be a space of distribution. That is essentially the message. So there is this very strange fact that I want to study probability, but I end up having to worry about distribution. Okay. All right. So let me just, as I mentioned, this is a very primitive version of all this kind of idea, but I wanted just to show that it's possible to get this picture. And with this technique, actually it was possible to obtain some result that were not known before for using Markov partition. For example, exponential decay of correlation for geodesic flow on compact manifolds in negative curvature. So this, the first breakthrough in this direction is actually the fundamental breakthrough was due to Dolgopiat, following some seminal work by Chernov, in which he managed to get exponential decay of correlation for some flow, but that was in the last millennia, like the paper was 98, and he was still using Markov partition, but then, he was just working for geodesic flow on surfaces, but you can get exponential exponential decay of correlation for all geodesic flow in negative curvature, and this was obtained just using in 2002, but just using this type of technique. And of course, the idea of Dolgopiat, but I mean, the language was not anymore in the language of Markov partition. So, because of course, that is the next step. You would like to analyze flows, and maybe, so that flows is just, if you look at flows, I am already in 3 dimensions, right? And let me just say one thing about flow. Imagine that you have now, so now we are in dimension 3. And when you are in dimension 3, what happens? I mean, let's consider the simplest example of flow. You have just, this is the torus, and then above the torus, you have some ceiling. Okay? By the way, this is an example that still we don't know how to do in full generality, although it's very simple. Because the basic property that made, that allowed to do this game was the fact that the geodesic flow is a contact flow. But in general, if you do a suspension over a torus, the flow is not compact. Even though the map in the base is symplectic, I mean, the flow is not a contact flow. So that creates some problems. And in full generality, there start to be results, but still in full generality is not totally understood. So the thing is like the dynamical system is like that. I go up with speed 1. When I get to the ceiling, I come back with the map F. And then I keep going up on speed 1. So this is called the suspension. Okay? So imagine that I want to study this type of system. And of course, you have to be, it seems kind of, okay, so what? I mean, it's kind of trivial, right? Because if you understand how the way the base mixes, then what is there to understand? But there is a basic fact that should scare you a little bit. Consider that the ceiling is flat. So it means that, you know, you go up, then the ceiling is flat now. And then it means that it takes always the same time for 2 points to go to the ceiling. So it means that if you take a set here that looks like this, an horizontal plane, this will just go around and around and around. There is no mixing. It never mixes in this direction. So even though the base map is mixing, the flow is not. So that's a little bit worrisome, because it means that the mixing depends from some subtle property of the ceiling. And there are examples by Ruel in which you can see that if you take, instead of constant, you take a piecewise constant ceiling, then you get arbitrary slow mixing. And of course, if the ceiling, it has some, now for example, there is some kind of very recent result by Suji, which shows essentially that for a generic ceiling, then you have exponential decay of correlation. But the ceiling should not be homologous to a constant, to a piecewise constant, and stuff like that. So there are some kind of obstruction. So the situation for flows is much more complicated than the situation for maps, and it is shown by the fact that while already in the 70s there were results on exponential decay of correlation for maps, I mean exponential correlation for flow, it happened only essentially at the beginning in 1998, essentially, with the work. First real result in that direction was the work of Chernow. Before there were some special cases, but it was really, there were like geodesic flow in negative curvature, in constant negative curvature. That was known. But that for negative curvature, so negative flow in constant negative curvature in dimension 2, 3 rather, for surfaces, then, I mean, you can use a representation theory and compute. So that's what we were doing. It was just an explicit computation. Exactly for this map, I can use Fourier transform and compute. But then you take the nonlinear version and you don't know what to do anymore. So that was, essentially, there was no idea. So how do you do in order to, I mean, can you kind of upgrade this business to flow? Well, you see, you have a problem, and the problem is if you got a little bit a general drift of what I was discussing, you saw that these computations that I did, they were essentially taking advantage of the fact that I had expansion in the system. Because essentially what I was saying, well, look on the stable direction, you have expansion, so things get kind of stretched and get smoother. In the stable direction, well, look at the dual. The dual also expands because the contract, I mean, if something contracts, you take the inverse, that will expand. And then in the dual will just also behave nicely. So you take functions that in some direction are nice and you use them as test function. And then in other direction, the function itself is nice. And then you just use that is smooth in that direction. So it's all based on the fact that there is some stretching in the dynamics. But in the flow dynamics, there is nothing. If you have a flow, if you have this guy is in front of this guy, you know, it's like they are like in a highway. I mean, between this guy and this guy, there are 10 cars. And for some reason, the street is so small that you cannot, you know, pass the car in front of you. Then you wait 2,000 here, and between you and this guy, there are still the same 10 cars, right? Nothing happens. So there is no stretching, no squeezing in this direction. This is just the flow direction. So it's clear that this technique per se will not work. You have to do something else. And there are a couple of ideas of how to handle this problem. But the simplest one is the following, that you now have LT. Now, because it's a flow, so instead of just having, before you had the transfer operator and you had a discrete semigroup, a discrete semigroup, that was this one. And now instead you have a continuous semigroup. And these are the transfer operator associated to the map, to the flow at time t. And of course, as this one has the property this one has the property just continuous semigroup. And so now you can say, okay, fine, I have this Banach space that works very well for maps, so let's just forget about this direction. I just write the norms that I wrote before, in which I control the stable and the unstable direction, and I see how this guy acts on this norm. And you discover that everything is more or less okay, but there is one thing that doesn't work. And the thing that doesn't work is compactness. Compactness doesn't work because you don't have any control. In the norm, you don't put any information about what is the regularity in the stable direction. And then this is like saying, okay, I have, I don't know, maybe you can try to play a little bit with regularity, but it's like saying I have C0 into L1. Okay, fine. So you have C0 into L1, but it's not compact in any reasonable way. So you lack this compactness business. But on the other hand, you can say, but okay, this is a semigroup. Maybe I can look at the generator. So if you look at the generator, you have to check that this semigroup is strongly continuous in this Banach space that you would like to use. And in fact, it is. Okay. So now you have a generator. So you have that the derivative with respect to t of LT rho is equal to some x, LT rho. And this x, what it is? This x is nothing else than the dual of the vector field. You know? There is a vector field, and so it's a derivative. It's not a bounded operator now. It's a derivative. Fine. But you have also some very nice formula, which is the following. Now, if you can say, okay, let's not look at the spectrum of this guy. Let's look at the spectrum of this guy. Now, this is not a bounded operator, but still, it may have a spectrum. Right? It's a closed operator because this is a strongly continuous semigroup. And so if I want to look at, this the spectrum of this guy, I have to look at the resolvent. So, and now, since you can see that you have some inequality of this type for this operator. So you know in particular that it's bounded in the future. So since it is bounded, you know that if that is positive, if the real part of this is positive, that this is invertible. And there is a formula for that. You can find it in any book. Okay. So you have a formula for the resolvent that is given by this integral, at least when the real part of z is positive, because this makes the integral converge, right? And now you look at this integral and say, wait a minute, but what was the direction that I didn't like? That was the flow direction. And what does this operator do in the flow direction is an integral. Okay, but that is compact. So this guy gives compactness in the flow direction. This is exactly what you missed. So it means that what you have to do, you have to study this operator instead than this operator. And this operator turns out that it satisfies, again, this kind of Lasota-York type inequality, and you have the compact embedding. And so you can essentially get information about the spectrum of the semigroup, trying to understand the spectrum of the generator. So this was more or less the idea that was used in order to study. I mean, it is still used to study flow, right? For example, there is a very recent paper that is just a preprint by Mark Demers, Vivian Baladi, and myself, in which we use these type of ideas in order to prove that if you have a billiard, a finite horizon billiard, so the particle does that, and then you look at the flow, then the flow mixes exponentially, which before was just known the Poincaré map, which is exactly the same situation here. You know that the base map is exponentially mixing, and now you want to know if the flow mixes exponentially. This is not obvious because of this problem of the ceiling. Yes? No, you get an information on the spectrum. You see, because you understand this operator, then you understand, knowing this operator and the spectrum of this operator, of course, means that you know the spectrum of the generator. Because if you know the spectrum of the resolvent, you know, you have to change z, you have to change z, right? Which stretch?
The way I think about that is that's just saying that now I'm going to flow for a random amount of exponential.
No. That's not. This is just, you don't have to think about dynamics. This is just a piece of functional analysis. The dynamics is always the same. This is just the dynamics. I go up, okay? So now I just forget about the dynamics. I have this operator, LT. I have this semigroup. I have a generator, and then I just know, I know that this is the formula for the resolvent, and now I want to study this operator. I don't want to have a dynamic. You can try to have a dynamical interpretation of it, but it's not necessary. I just say, okay, this operator, can I study it? I say yes, because I have this inequality and I have the compactness. So I know the spectrum of this operator, and now you can, if you know the spectrum of the resolvent, you can map it to the spectrum of this guy. So essentially what you do, the spectrum of X will be like that. It will be 0, which is the invariant measure. And then, for example, imagine that you take 1 as Z, and now you look at 1 minus X minus 1, and you look at this spectrum, okay? So what it will happen? This spectrum will have, of course, in 1, it will have an eigenvalue, because if X is 0, then this is exactly 1. So this guy get mapped to this point. And then, I get some information of this type, that the spectrum of this guy is contained here, and it is quasi-compact, so it has some part that I do not control, and here there are only finitely many eigenvalues. And now I have to map this into the spectrum of X. So it's just a transformation on the complex plane, right? And then the inside goes outside, and so I get some, you get that the outside here get mapped in here, and this smaller disk gets mapped in a larger disk. And so you get the information that in this part, you see this eventual eigenvalue end up here. Okay, so you can have some eigenvalue here. Here you know already a priori that you don't have any eigenvalue, so it means that you can map back and you know that here there is nothing. But then in principle there can be some eigenvalue here. But since they are only finitely many, then you have learned by studying this operator that in this part of the complex plane you have only finitely many eigenvalues that are far away from zero. From zero. And now you say, okay, but I mean, this is just a small part. Okay, fine, but now take z equal 1 plus alpha I. Okay, and now you study this operator. They are all the same. You have to study this operator for all z, of course, for all z. And then you get something similar, and so again you get that here there are only finitely many eigenvalues. So finally, you keep doing it, and you discover that there is a strip in which eigenvalues do not accumulate, and the essential spectral radius is over there. And then you have the problem that, okay, but here still they are countably many, and they could accumulate going to infinity. And this you need some extra estimate on what. Now you have to estimate what this operator does when this z has a very huge imaginary part. And that, of course, is essentially what it is. It's an oscillatory integral. And then you have to show that this, it oscillates, there are some cancellation. If there are some cancellations, then the spectral radius here is smaller than 1. And then if you can show that when alpha is very big, the spectral radius of the operator is strictly smaller than 1, then it means then when you map it in the complex plane to see the spectrum of sigma, the spectrum of X, then here there are no eigenvalue because the exterior of the disk get mapped in the interior. And so here, this is just the resolvent, so here there are no eigenvalue, and the eigenvalue can be only in the rest. But then you move it, and then you see that here there are no eigenvalue. And so you get that the final picture for the resolvent is the following. There may be some eigenvalue, there is some line here, the essential spectrum is on the left, here there are some eigenvalue, and that's it, finitely many. And then you have, this is the spectrum of the generator, then you can see that the semigroup, it will be, there is a spectral gap now, right? So the generator has a spectral gap, then the semigroup, you expect it to be exponentially mixing. So that is kind of what you have to do, but it takes a little bit of work, right? I mean, and this part here of analyzing what happened for so you see, it's done in two parts. Once, you just use this Lazotta-York inequality, and that gives you the fact that here you have a strip of finitely many eigenvalue. But because you see, if you look at constant curvature, then this spectrum is the spectrum of the Laplacian. So you know that at a certain point you have really a line of eigenvalue. So you cannot hope to show that there are only finitely many, because this is kind of big. It contains this line. Okay, so what you want to show is that if you get close enough, at a certain point there are no eigenvalues. This needs an extra argument that is based on the fact that this is an oscillatory integral and there are cancellations. And this is Dolgopiat argument. I mean, that was invented by Dolgopiat, and essentially everybody else more or less copied it, but Suji that has a different version in which you exploit a slightly different mechanism. Okay, that is the situation. So that is more or less what I wanted to say. Oh, I'm done, just done. Okay, let me just finish last 5 minutes, just making just a further comment on what So this is, in some sense, if I forgot what title I gave for this upcoming conference, but I think I will talk about this. So this, in some sense, is a preview of my talk at this conference that will be in two weeks or so. And the point is the following. So always in this direction of wanting to go toward more statistical mechanics, reasonable models, there is another big ingredient that is missing in this picture. Now you see we're getting a little bit close, because now we have a flow. There is an error-preserving flow, so start to be a little bit like a gas of particle. But there is a key ingredient in statistical mechanics that here is not very much present, and this key ingredient is conservation quantity. Okay, so in statistical mechanics you have like the energy is conserved, the mass is conserved, the momentum may be conserved. I mean, there are this conserved quantity, and the crucial fact of this conserved quantity is that they evolved on a different time scale with respect to the microscopic degree of freedom. So in some sense, if you want to go a little bit further, you should somewhat try to understand what happens in systems that have at least 2 time scale. And that is missing in this picture. And that is kind of, in some sense, a serious problem again, because if you have some variables that move very slowly, then these variables that move very slowly is a little bit like the flow here in some sense. It's not really, but it's a direction in which you don't have really expansion and contraction, because there the dynamics is very slow. So in other direction it expands and contracts, maybe, okay, fine, but in this direction in which you have conserved quantity, it does not do much. And so it's not really clear. It seems that you cannot handle it with this philosophy of seeing some kind of spectral gap or stuff like that. So, so my point of view was just to try to make, again, a very, very simple system in which you have this phenomena and try to analyze it to see if one can do something. So this is the simplest example I could come up with, dimension 2. So this is a map from T2 to itself, and the map is this one. And the derivative of x is always bigger than lambda, bigger than 1. So what it means? It means that x is my fast variable. And for my fast variable, I take the simplest, again, possible dynamics I can think that has this property of expansivity, of instability with respect to the initial condition, which is an expanding map. But only now is a family of expanding map, because it depends from another variable. And this other variable is my slow variable. It changes very slowly. There is an epsilon here. So this is the time scale. So if epsilon is equal to 0, this is just constant. The system is not ergodic, because theta doesn't change. And so you can think of it as theta being the, of course it's nonsense, right? But morally, you can think as theta being the energy. Okay, these are maybe the position and the direction of the velocity. And this one is kind of the current that tells me how the energy changes, right? So of course it's complete nonsense. This is no Hamiltonian structure, no nothing. But morally, that is what this map is intended to capture as a mechanism. And it seems to me that if you do not know how to handle such a simple system, then it is very hard that you can get the possibility to study a system in which you have energy transport and stuff like that. So that is some thing. And again, you see the direction. So there is something, let me tell you. So this system is called partially hyperbolic. What are partial hyperbolic systems? Hyperbolic systems are these systems in which you have expanding and contracting direction everywhere. Partial hyperbolic, it means that your phase space, instead for partial hyperbolic system, you can take a point and look at the tangent space at that point. And the tangent space, you can split it in one direction in which the dynamic expands and one direction in which the dynamic contracts, exactly like here. Well, here it's kind of stupid because the tangent space and the space is the same because we are the torus, so the tangencies are 2. But, I mean, in principle, that is the idea. But now, partial hyperbolic, it means that the space is split, the tangent space at each point is split in 3 sub-bundles. One you contract, one you expand, and in one you don't know. And this is exactly the situation here. Well, the contracting does not exist, so it's empty. But there is one expanding direction, more or less, that is more or less the horizontal, the x direction. And then there is a vertical direction, which is, so this is x, this is theta. So there is this direction here in which you don't know what's happening because this dynamic is very, very slow in this direction. It's not clear. Yet, it is there is kind of a, so this is somewhat, these partial hyperbolic systems are the next step. If you want to understand the system with conserved quantity, you have to understand something about partial hyperbolic system. So there is a lot of work about partial hyperbolic system, especially from the Brazilian school or people like Pug, Schub, Wilkinson, I mean, that come from a more like Bowen tradition and stuff like that. I mean, there is a lot of, but it's more geometrical. There are not many results on statistical property. But geometrically, something is very well understood. For example, this system, you know that it has what is called the central foliation. So it means that there are closed curves that foliate the torus, okay? And these closed curves are invariant, so by the dynamics. So it means that this curve is mapped to this, and they are invariant. So there is an invariant vertical foliation, okay? And so you have that in this direction, you have expansion, and in this direction made of closed curve, well, it is not very clear. You cannot have expansion, right? Because it's closed curve. So if it would expand uniformly, then this will get longer, and then you cannot stack it back on the torus. If it contracts uniformly, then it's the same, right? It gets shorter, and then it would pinch the torus. It's not possible. So it's clear that here something complicated must go on. You must have some contraction, you must have some expansion. It's something more complicated. And there is an extra, and then there is, you could have the naive point of view that, okay, I take this foliation somewhat, and I kind of use it to divide my space in 2 directions. One, I mean, I use it as a coordinate system, right? So I take this to be straight, essentially. I use coordinate in this direction and coordinate in this direction. And then in this direction, I'm kind of invariant, so maybe I can do something. But then you discover that in many situations, it happens that this foliation is not absolutely continuous. The leaves are smooth, but the foliation itself is not absolutely continuous. It means that you can take 2 lines here, you take a set here, A, of positive measure, then you move along this foliation, and here you get another set, which is the image of this set along this foliation, and this has 0 measure. It's kind of difficult. I mean, I cannot picture, right? I mean, something like that. But that is what it is. This is a foliation that is only older in general. I mean, when I change, if I take this vector, this tangent vector here, and I move in this direction, I see the tangent vector to this leaf, the tangent vector to this leaf. I get a vector field along this line, and this is only an older vector field. So the foliation turned out to be not absolutely continuous in certain cases, and if the foliation is not absolutely continuous, my idea of using it as a coordinate system is nonsense, right? Because nothing will work. So there are considerable technical problems in this situation, which need several ideas, but I am over time. Let me just tell you one last thing and I'm done. If you take and now you look at theta epsilon, theta t epsilon equal to theta epsilon t. So this is exactly, because you see, this is exactly, you look at it and you see that if this would not depend on theta, then this and this would not depend on theta, this will just be the sum. The advantage in this variable will just be given by the sum of this increment along the trajectory of this variable. So it is an ergodic sum. So then it is very similar to what I've been doing before. It looks like if it is an ergodic sum, then you should get some kind of law of large number, and then the correction will be central limit theorem, and so on and so forth. And so it makes sense to say, okay, I rescale these dynamics, because I know that I have to wait a time epsilon minus 1 in order for this variable to have a change of order 1, because each time I increment of epsilon. And then I wonder if this will have a behavior that I can describe in some effective manner. And the result is that this, the behavior of this is very, very close to the behavior of this differential equation. So this omega bar is just, so each map here has its own invariant measure. Let me call it with density rho theta, and the invariant measure is mu theta of phi equal the integral of mu theta phi. Because this is an expanding map, so it's exactly what I discussed in my first class. Each such expanding map has a unique invariant measure absolutely continuous with respect to Lebesgue. And so I can take the average of omega take this average, and I get some average vector field, and it turns out that this, the probability that these differ from the solution of this differential equation for a time that is pretty long, for a time that is of the order epsilon to the minus alpha, the probability is small in epsilon. This is stochastic. This is like Venstre-Friedel system, right? It's just a dynamical system. This is given by the law of large number for this variable, because I just sum this quantity, epsilon minus 1 time, so it's like an average. Okay, so this is given by law of large number. Then I have a correction that comes from the CLT, and that correction is of order square root of epsilon. So this is essentially a stochastic differential equation a la Venstre-Friedel, and it is possible to show with some effort that this guy is close to this one for a time that is longer than it's not just order 1, but for a time that is some inverse power of epsilon. Okay, so, and for a time, sigma z is the variance of this variable with respect to this. So, sigma z is the following. It is the variance, you fix theta, then you have the map f theta of x is equal f x theta. This has an invariant measure, invariant density that is rho theta. And if you take this sum, okay, just fix theta, and now pretend that you have just a fixed dynamics. Now this is exactly what should converge to a random Gaussian variable, and we'll have some we'll have some variance. So if you compute the variance of this random variable, that is exactly sigma z. Z is theta, right? I mean, yeah, sorry. I should write theta here. I mean, okay, let's say z, and what I say is that this is more or less zt. More or less, it means that there is a coupling between the two, and the distance between the coupling is small. I mean, the distance in the coupling is small. But the key fact is that these are closed for a time that is long. It's not just for time of order 1. They are closed for a time of order epsilon to the minus alpha, for some alpha. And in that time, these depend from what it is. But if this one has, for example, only one sink, then in that time, this will go to equilibrium. So since the true dynamical system is close to that, then you know that the true dynamical system goes to some measure that you can understand. So that is kind of, but I mean, of course, in other cases, not, no, because these has state that are, how do you call this state, that are not stable, but metastable. This may have metastable state, then it means that your dynamical system will have metastable state. So essentially, you can do some kind of Wenzel-Friedrich theory for this deterministic dynamical system, just copying what it is done for this one. But, sorry, I went over time. I'm sorry. Finished.